G, and you have to specify representation of the Wilson loop transform. Physically, the Wilson loop inserts an electrically charged probe massive particle into your theory, which you can use to probe the state of your theory. And what it has will give rise to interesting questions is that Wilson loop operators depend on the precise nature of the gate. So you can only talk about this. Since the Wilson loop is defined by representation, you have to really use the label of the gate. Yeah. But this raises the existence of this very elementary and basic object in gate theory raises an immediate puzzle or challenge for dualities, both for field theory dualities, and also for quadratic dualities, gate gravity dualities. Which essentially is what is the dual description of Wilson loop. These operators are leaflets. A series of the questions that you should answer if you think about duality is to have an understanding of how Wilson loops map and duality. And actually, this challenging is even more of a challenge that raises a puzzle, which is the following: is that we are accustomed to the fact that global symmetries and Boost anomalies of dual field theories must match. Global symmetries must match the dual theories, but we know that gate symmetries will not match. In some sense, gate symmetries, and there's a famous rule in gate symmetries are not symmetric, they are redundancies. So how can it be? And in particular, under dualities, typically the gate groups are radically different, especially in the case of the discussion today. But yet, Wilson loops play over the representation of the gate group. So somehow the dual theory must know somehow about the representation of the gate group, even though the dual theory may have a completely different gate group. In the examples that we know in field theory dualities, gate group in dual theories can be radically different. So we have two dual theories A and B, and the gate group can be completely different. I will provide examples of that. And even in quadratic dualities, you can see the examples because on the gate theory side, you have a representation of the gate group, but in the bulk, there is no lead group structure anywhere inside. Nevertheless, the ADS dual has to somehow be able to generate a representation of the gate. So in this talk, we'll be answering all these questions for a particular type of infrared duality in 3 dimensions known as a mirror symmetry. So this is the duality, the extreme infrared behavior of two completely different 3-dimensional ultraviolet gates that flow in infrared in the same fixed point. And what we will find is that the dual description of Wilson loops in one dual theory is described by some operator that is defined in a more subtle way than Wilson loops that we call by beam to be the working group operator. So we'll see that somehow, even though the dual theory will not have a gate group G, GA, we will nevertheless be able to construct for every Wilson loop operator a line operator that is labeled with the same data. And what we will see is that this dual line operator, the dual of the Wilson loop, is defined by coupling a very specific one-dimensional gate theory that lives on the curve over which the Wilson loop was originally defined. And this one-dimensional gate theory, and of course, this one-dimensional gate theory will be coupled to the bulk. We will have a 3-dimensional field theory, and we're going to couple a one-dimensional defect to that theory. And this will be the dual description of Wilson loop. And we will find that even though the dual theory has a very different gate group, we will be able to encode the original representation of the Wilson loop in the choice of gate group and matter content of the 1D theory. So in this kind of duality, even though the gates are completely different, the dual theory nevertheless knows in a subtle way about the representation of the gate group. And we will give a very explicit algorithm of how to construct the mirror map for group operations. Here I use a caricature. In details, this map can be complicated, and I will show you some examples of what this map can do. Okay, so let me tell you a few things on mirror symmetry, just to set up the background. So this is an infrared duality that relates the IG flow of two 3-dimensional electron swirl theories. These are theories that have one half so this is the thing that two theories that we define at very short distances, in terms of 3-dimensional gate theory, flow in the same infrared and the same fixed one. These ultraviolet theories are defined in terms of the usual multiples of theories with supercharges that naturally start their life in 6 dimensions, just like theories with 60 supercharges naturally start their life in 10 dimensions. So the UV definition is in terms of some theories of vector multiples and vector multiples. So let me tell you a few things about the basic things about mirror symmetry and how it works. So this two-dimensional gate will have a rich space of ground states that in particular contain 2 factors, which is the Coulomb branch and the Higgs branch. Essentially, these are the factors where either vector multiple fields get vacuum expectation values or hypermultiple fields get vacuum expectation. So this gives rise to some manifold of vacuum that these theories have. So let me give you an example of specific examples of mirror dual theories. So these would be 2 different ultraviolet theories that flow. The conjecture is that these 2 theories flow in the extreme infrared and fixed one. So here's an example. We have U2 super QCD with 5 fundamentals being dual to some Weber gauge theory. So here I'm using the standard notation by now of how to encode the gauge theory in terms of some diagram. Where each block, each circle gives you the gauge law, each block gives you a fundamental matter multiplet, and each line here is a bi-fundamental matter multiplet. So as you can see, for example, under duality, the gauge group of these theories is radically different from here. The rank don't even match. So this was have to be compared with S duality, with Montaner and all duality for dimensions, where the gauge groups can be different, but at least the rank is the same. Here, the rank doesn't match. So as you can see, the gauge group of mirror dual theories can be very, very different. Now let's explain a little bit about the infrared fixed point that these 3-dimensional gauge theories are supposed to flow to. So these theories have a very, in general, a rather large, rich global symmetry, GC and GH, which you can think geometrically as isometries, the isometries that act on the Coulomb and Higgs branch and back theory. This infrared conformal field theory can be given canonical relevant information that are associated to the global symmetry theory. And they're defined by turning on mass parameters for the global symmetry associated to the Coulomb branch. So these are particular operators that you can define abstractly in this infrared conformal field theory once you know what the global symmetry theory is. These deformations are important in order to understand how under mirror symmetry, deformating by one operator, how it is related to deforming the dual theory by two. So one of the basic things about statements about mirror symmetry that was not work is that under mirror symmetry, the space of Higgs and Coulomb vacuum exchange between 2 mirror theories, and the deformation of the theory by a phi or mass parameter is equivalent to deforming the mirror theory by the opposite parameter. So you change phi area with deformations with mass deformations. But here we're interested in understanding what is the story with line operators in this duality. As I said, this 3-dimensional gauge theory is talk about gauge theory, so they definitely have rules to look if you want to understand. Okay. So the first thing we'll do is just basic kinematics to understand what kind of beasts can exist just by analyzing what the symmetries of these theories are. Okay, so let's study what are the possible line operators that you can have in a 3-dimensional equals conformal field. So the superconformal symmetry of the 3-dimensional equals 4 field is always H4 is less 4. Okay? So this is the 3-dimensional equals 4 version of the famous SU22 is less 4 and equals 4 squared. Now we want to study line operators in this theory. So as you know, if you have a line in R3, you preserve this match symmetry inside the conformal. And if you further demand for be able later to do computation that your line operator preserves some symmetry, some supersymmetry, there are 2 different ways of combining the unbroken symmetry of the line with supercharges such that they're embedded in the place before as well. So there are 2 different line operators characterized by different preserved symmetries. One little by this supergroup and one little by this supergroup. Importantly, one of them preserves the U1C times U1 and U2H R symmetry theories have. These theories have an SU2 sequence situation symmetry, and the Wilson rules break one of the SU2 to a cartan, and the W symmetry preserves the G1C, and the B symmetry preserves the G1H. And what we want to do is to provide, so there are two types of operators that are defined in a given theory, in a given case theory, characterized by these symmetries, and what we want to do is to provide a UV description of these operators. So right now, the infrared theory, I want to give a UV definition, a short distance definition of this operator, and understand their mapping and their duality. So at short distances, of course, the theory is not conformal. It's defined by a ultraviolet case theory, which is super normalizable. So one thing that we can try to do is do the same problem of understanding what are the line operators that you can have in an ultraviolet conventional case theory. And to cut the story short, there are essentially two different supersymmetric line operators you can define that are also characterized by the supercharges and asymmetry that present. Of course, the asymmetries are the same as the ones you have here is that you start with a three-dimensional theory in the ultraviolet, which is concurrent invariant, and in infrared flows to a fixed point. In the ultraviolet, I can define two different line operators characterized by two different sequences, which in the infrared flow to two different superconformal line differences. So this is the kind of class of this that you can define in line operators you can define in two dimensions. Okay, one important observation that I want to make that is key in answering the question that I motivated at the beginning of the talk is to notice that both types of ultraviolet light defects can be constructed, can be given a UV definition in terms of coupling dimensional theory to a to the three-dimensional column theory. And obtained explicitly by gauging, so you have a one-dimensional theory that has some global symmetries. And you can define the operator by coupling the 1D theory to the bulk, by gauging the 1D flavor symmetries with the 3D gauge fields in a very particular way. So this will define a line operator. So these are some details. So now, in order to define so remember that I said that you read there are two types of line defects. So therefore, there have to be two different types of one-dimensional theories that I can write down and couple to the bulk theory that will give rise to two different types of line operators. So for the SQMP line operators, so remember this specific line operator in the ultraviolet, what I can do is construct the 1D theory. It's a one-dimensional supersymmetric quantum mechanics that can be obtained by dimensional reduction from 2 dimensions 0-4 supersymmetry. While SQMP, which is the other kind of line operator that we can do, is obtained by dimensional reduction either from 4D n equals 1, so the standard was a binary story, or you want to use kind of the more democratic language, is the 1D n equals 4 theory that we get by dimensional reduction from 2D to 1. Both types of line defects have a democratic representation in terms of particular supersymmetric coupled to a bulk. I will have to explain how this works for the simple case of the Wilson loops. So Wilson loops are usually described just by integrating some holonomy over some curve. But I think that's interesting, and we will make a very heavy use of, both in motivating the duality and then actually in constructing the dual map, is that you can always write down a Wilson loop in terms of coupling a particular supersymmetric quantum mechanics to a line, to the line that the Wilson loop is supported. And then what you can show is that by integrating out the degrees of freedom that are supported on the line, you insert the Wilson loop. So this is a convenient way to think of Wilson loops, because that's exactly how the dual operator will be described, except that it will be a different supersymmetric quantum mechanics.
So, Jama, should I think of this quantum mechanical system as some D0 brane? Is it D0 brane?
Well, when we come to the right setup, it's not going to be D0 brane, there will be some kind of brane. So this will be, but the more precise tell is that this quantum mechanics is not D0 brane. It's the degrees of freedom that arise from quantizing open strings between two types of branes. So when you quantize the open string between two types of branes, it will give rise to some degrees of freedom that localize on the intersection. And if you integrate them out, You will see, this is coming. And actually, what I want to make is that this defect field theory representation of a Wilson loop is actually something that is naturally given to you if you look carefully under the hood about how string theory gives you a representation of Wilson loop operators in terms of branches. String theory gives you a Wilson loop, not directly in this form, but in the form of a quantum mechanics coupled to the ball. And this we'll be using heavily. So this is about Wilson. Every time we do it about the more exotic and newer defect loop, we will call vortex loops. And you will see them in the next one we call them vortex. So this guy is constructed by coupling the bulk theory to quantum mechanics, which as I said is obtained by the four-dimensional equal one theory. H by the bulk fields. And in general, I can also allow superpotential couplings between the matter fields of the bulk and the matter fields of the boundary of the defect. And then at the end of the day, the particular vortex operator has a nice representation, again, in terms of some glorified Weber diagram, a mixed 3D, 1D Weber diagram, that tells you how the 3D theory couples to the 1D theory that is here. So these symbols tell you, for example, this theory has a particular flavor symmetry, UN minus 1, UN minus 1. And this picture, for example, tells you how the UN minus 1 symmetry is identified with the UN minus 1 gate symmetry. Remember that I said that circles have to do with gate symmetries and squares have to do with global symmetries. So this particular operator could be defined by gauging a one-dimensional equal source symmetric quantum mechanics. It has a UK gauge group with an adjoint hypermultiplet, where you gauge the n-1 flavor symmetry that rotate chiral multiplets of the defect theory with a UN-1 gauge group, and where you identify the flavor symmetry of a UN-1 chiral multiplet of the 1D theory with a UN-1 flavor symmetry of rotating hypermultiplets in the bottom. So this completely defines the 1D theory, and this path integral, the path integral over this system defines a voltage loop. Just like in the previous example, the path integral over the localized degrees of freedom gave rise to. Here, what you get is something much more subtle.
Is that a simple definition without supersymmetry?
Yes, because this is implicit, well, three-dimensional implicit. Yes. No, supersymmetry is not needed at all. All that you need is to specify the couplings of the quantum mechanics of the ball. The reason I'm doing supersymmetry here is that later on, I will be able to, so we'll make the conjecture of the quality not is, and learn to check it. It is an extremely long energy flow. It's not something you can do in perturbation theory. So the reason I express is that I can use localization to compare the answers of the expectation model. But of course, I can define it in non-supersymmetric theory. This object exists in non-supersymmetric theory. In a way, this story that I'm going to share is a non-Argelian version of what condensed matter physics is called particle vortex duality. So it's definitely something that exists. Okay, so what is the physics of this crazy Lagrangian? So if you look more carefully under the hood, what you find is that essentially integrating out the localized degrees of freedom that live on the defect, what it does is create a singular magnetic field for the bulk field. If you have a three-dimensional field, the line is codimension 2. So what you have is essentially a localized magnetic flux supported on the loop, which is precisely the field configuration of the singular vortex. So you have just a delta function. So in the semi-classical ultraviolet description, you have a singular vortex configuration. So what you've done in the electric case, in the Wilson loop case, I inserted an electrically charged particle, which was a probe. Here, this is what I'm inserting is an operator that is a probe vortex, heavy vortex. And therefore, that we call that vortex. So if this is like by mirror symmetry, so now let me see some qualitative things after this analysis of symmetries and what you can write down to tell you how mirror symmetry should work. And then we'll have to see how it works in detail. One thing is different levels of approximation of how you get to the answer. So the first element is that we have these two UV theories flowing infrared to the same fixed point. We notice that the symmetries of the two supersymmetric quantum mechanics are exchanged under the exchange of SG2C and SG2H, which is one of the basic operations that mirror symmetry does. It changes the action of the asymmetry in the Coulomb band to the action of the asymmetry in the Higgs band. And therefore, what you expect qualitatively just based on the symmetries is that the Wilson loops of one theory map to the vortex loops and vice versa. Just because these guys have the same symmetry. But now, this is all very qualitative. The question is, the question I already started with, how can it be that these two theories have completely different cases? How am I going to encode the data of the representation of the Wilson loop in the dual theory? And then the even more detailed question is, what is the concrete mapping? You have a set of operators, you want to construct a mapping. How are we going to do this? So the way we can answer this question is by relaxing and letting yourself be guided by what string theory is trying to tell you. So what you have to do is just relax and let the string theory tell you what the answer is. And you get an answer. And then you get, if you don't like, if you don't believe it, you can check it using localization, which anyway you go. But anyway, so what is the basic idea? The basic idea is that all these dimensional equals for that we've been discussing can be realized at the low energy effective field theory that live on brane and string theory. So just as n equals for square meters is the low energy theory on NT3 branes, three-dimensional equals for theories live at the intersection of certain type of branes in string theory. So if you're not familiar with branes in string theory, the details of which branes are and how they are rated is not very important. But the physics is the same as standard equals for square meters. There's a brane intersection where you look at the low-lying modes, low-energy modes, you get the dimensional equals for theory that's going to be supported in this. And these little branes are oriented in some way, and then you have a whole bunch of Schwarz 5 branes and D5 branes. Now, depending on whether the extra direction of the D3 brane is aligned or a circle, the gate state that we realize from this brane configuration is either encoded into a gate state that has a representation in terms of a linear quiver or a circular quiver. So these are complete 2B dimensional n equals 4 theories that you can write now. One thing that's very nice and usual with string theory, if it's anything, is that it geometrizes all the symmetries and parameters of the field theory. So any question that you wanted to answer before about what is the modular space of vacuum, what are the parameters, and so on, has an extremely elegant description in terms of geometry. You just have to kind of play Sudoku with branes, and any question you have about gate theory can be translated into a question about branes and moving branes around in 10-dimensional space. Okay, so this gives you the UV definition of a three-dimensional equals 4 theory. The observation, so as noted by Hanani Witten already many years ago, of course, in the aspect of group operators, what they notice is that once you have a particular UV realization of a three-dimensional equals 4 theory, you can ask, how do I get the mirror dual theory such that the two theories flow in the same fixed point? And what they found is what we have to do is to perform S duality on this brane configuration. So S duality is a symmetry of type string theory. So this is in type string theory. And then what you do is you start with a brane configuration where you can easily read off. If you study a couple of chapters in Polchinski, you'll be able to read what the gate theory living on this defense is. In order to construct a mirror, what you do is you have to perform S duality. But now when you perform S duality, the branes are meant to rearrange the branes in such a way that you bring it back to this canonical brane configuration. You can really easily read off that, for example, here is a UN1 in the gate signature. So I playing this game and take into account that when you cross branes, you can have the phenomenon, it's called brane creation, where when you change, so when you perform S duality, you will have to cross, to go back to the canonical brane configuration, you will have to cross D5 and S5 brane. And what can happen is that as you cross them, a D3 brane is created just to conserve flux. Essentially, if you do flux conservation, you may have to create D3 branes and have to keep track. And that's why the ranks change, essentially, because as you move the branes around, the mirror gate theories will have different ranks because you have to create or destroy D3 branes, which is the branes that support the gate. Anyway, that's all I have time to say for now. So now, what's the basic idea of how do we get to the answer of this? Or once we have the kind of the more kinematic analysis at the beginning. The basic idea is extremely simple, is to try to give a brain representation of Wilson loops, enrich the ring configuration that I started with, such that we add extra brains that insert the Wilson loops. And this is a generalization of something I did with my students many years ago, which was, again, motivated by the question of I started with, which was, in igst2015, you can have those first parameters that has Wilson loops in any representation R. How do you find the Wilson loop in the buffer? So it's essentially the same question as that was for the case of igst, for the case of mirror symmetry. And then what we found is that it's described by brains, and the way to understand it is by starting with representing Wilson loops by adding brains to your, in that case, was n for first parameter, in this case, this dimensional equals 4 case. So how do you insert a Wilson loop into gauge series to realize from brains? So I think the basic idea is you have to insert a probe of electric charge for the Wilson loop. It's some electric source. And again, if you study the two relevant charges of voltage, you know that the endpoint of the string, from the point of view of the brain, is an electric charge. So when you combine your fundamental strings and on your gauge loop, so you have this where your n equals 4, or in this case, n equals 4 to the lead. You have a stack of fundamental strings ending on this guy. And then the choice of representation that you're injecting into your gauge theory is dictated by how you by which brain define n on the other end of fundamental strings. Here, and the reason that that's the case is that what you have to do, you have to determine the representation. That's what we did essentially with Castellini, is to study the quantization of the open strings between the discrete brains and discrete brain far away. This will tell you, once you integrate the user field, will tell you which Wilson loop you have. So, what we showed in this particular case is that if you have k fundamental strings stretched between discrete brains and a D5 or D5 prime brain, D5 prime brain is just a D5 brain in a different orientation. You have k fundamental strings from the point of view of a down-to-earth gauge theory person, but this means that what you do is you're creating k particles at minus infinity and inflating them at minus infinity. And what you're doing is integrating out the localized degrees of freedom that you got from the 3-5 strings. And what you can show in a relatively way involving anomaly and global anomalies and so on, I don't have time to go to that, is that if the brain far away is a D5 prime brain, what you get is exactly the Wilson loop in the symmetric representation, and if you have a D5 brain, you get the Wilson loop in the symmetric. And it turns out actually that you can also find a one-to-one correspondence between the weights of the representation and the configurations of strings that can stretch between D3 and D5.
Are these semi-classical?
Sorry?
Are these fundamental strings somehow semi-classical, or are they just the fluctuations that you have?
So this guy, okay, so no, these are heavy strings.
These
are heavy strings. So these guys are the fluctuating open strings between the D3 and D5.
But those were always there.
Sorry?
They were
yes,
always there.
I mean, what I'm saying is that I'm integrating them out. Not in the backend configuration, but in the configuration where I have k static strings in there. If you want to find a Farsian representation, I don't have to understand. You can easily generalize the symmetric and the symmetric by adding more stacks of strings and D5 red and blah blah blah. Forget about this for the moment. Good. So now, so this is how we're going to go about it. So now what I want to do is to find, so this is the description of the Wilson loop. I just gave you a fancy description of Wilson loop in terms of brain, but the thing that this buys us is that now I use the intuition that mirror symmetry is S-duality, and now all I have to do is perform S-duality on the enriched brain configuration. So I have a stack of brains with fundamental strings that perform S-duality. The original bulk brains come back to themselves, and the fundamental strings become this string. But now the thing that's important is that, unlike the fundamental strings on these strings, open strings ending on these strings support gauge theories. Okay? So on this defect, the D1 brain, I have a one-dimensional gauge theory. And this is the one-dimensional gauge theory that we were talking abstractly about a few minutes ago. So now, how am I going to construct the mirror description of the Wilson loop? Yes.
Suppose that the D5 know that the gauge loop
this is so this open series has two ends. It's a bifundamental string. It's a fundamental of the defined. So when you pass integrate over them, you get okay, I didn't say it here. This is the trace over the UN group near the difference. It's not because the string has to reach the canonical range configuration where we can read the word gate theory, but now we're going to get this enriched with D1 ending on this configuration. And we will have to learn how to deal with the fact that now we have to rearrange the 5 brains around while we have extra D1 brains in the game. So that's something that we figured out. And I'll tell you more or less what the answer is. Now, one thing that you find that you end up with a brain configuration that describes the mirror gauge theory with these strings. And it turns out that in order to read the gauge theory, that these strings, this again is one of the basic rules about brains and string theory. In order to read the gauge theory that lives on the D strings, you have to let the D strings end in Navier-Schwarz 5 brains. But now you have these strings that ended on D3 brains. There is a Navier-Schwarz 5 brain on the left and one on the right. So there are two different ways in which you can read the gauge theory. You can either move the D1 brains to the NS5 on the right or on the left. And this gives you two different 3D1D theories realizing the same vortex loop operator. And the type of gauge theories that you get by playing these games are one-dimensional n equals 4 gauge theories of this type. So these are unitary, so one-dimensional equals 4 theories with unitary gauge loops with bifundamental chiral multiplets. You can have adjoint chiral multiplets, and on the end node you can have some fundamental and fundamental chiral multiplets. And the detailed representation of the vortex loop is encoded in these numbers. In a combinatorial way, it's simple, but I will not explain in detail now because it will take too much time. For the symmetric representation, you can obtain it just by a single node with an adjoint, and for the antisymmetric, it's with a single node without it. Good. So I already told you the rules in principle how to do it. Just perform S-duality on the rules on the brain recognition describing a particular Wilson loop. Move the brains around. Be careful what you do with the D1 brains as they grow to 5 brains. And you will end up with a specific 3D1D gauge theory from which you can the roots defines the dual vortex loop operator. And importantly, the zero-order question about the representation is answered by noting that the representation is encoded secretly into the ranks of the 1D gauge theory. Not only the rank and the matter content, whether you have an external or not. So let me give you, so if this sounded at the start, let me give you a concrete example of how you do this. I just chose the example because people like it, which is a particular three-dimensional four-theory that's called T of S-UN. It's also a theory that has a very peculiar property that's very unusual, that is self-mirror. So the mirror is itself. And the reason I chose those is because this is a very nice fan of n equals 4 superior method because people have a lot of n equals 4 superior method. Okay, so let's start with the simplest kind of Wilson loop, or the one that has the simplest map. Let's consider a Wilson loop. So what is this theory? This theory is a theory of U1 times U2 up to UN minus 1 gauge group. And in the last UN minus 1 gauge group, you have n fundamentals, charge fundamentals. So let's consider Wilson loop in this node. Okay, so I can consider Wilson loop here. This is realized in the brain picks in a very simple way. So what I have to do is consider the randomization. I have n defined brains here. I have n minus 1 D1 brains ending between the 2 labs and S5 brains. And all that I do is I stick the Wilson loop by having fundamental strings ending on it. And here I chose D5, which means that I'm setting up Wilson loop in a symmetric representation. All I have to do now is just follow the rules. I perform S-duality, and then I rearrange the brains back in a way that I can read easily. I go to the canonical brain configuration where I can resolve the dual case. One thing the reason that I chose the example first that makes it simpler is that in order to go from here to here, so this is the original gauge theory with the Wilson loop, this is the final gauge theory with the vortex. The reason I chose the example first is that in order to go from here to here, I never had to cross 5 brains per D1 brain. Actually, it was And then I can very easily here we talk what the 1D gauge theory is. What the vortex loop dual is. So depending on whether I let the D1 branch end on the right or the left hand side branch, I get two different descriptions of the vortex loop, which is, and now you can read from this brain picture exactly what is and how the 1D theory couples to the 3D theory. So what you find here is a particular 1D theory that whose flavor symmetries are gauged in this way. And notice that if I choose the other representation, I have the, the physics predicts that this is the same operator, but it's represented in a different way. You have a different, well, you have the same 1D gauge theory, but that couples to the 3D theory in a different way. Notice that the way that the flavor symmetries are gauged is completely different here. But one thing that that happens is that actually these two descriptions, which can be checked to see what are just two more descriptions of the same infrared line operator. So this was for the simplest case where I don't have to worry about branch crossing these strings. The most complicated case where for an arbitrary 3D post theory will already happen when you want to consider a Wilson loop, not in this node but in any of these other nodes. Here you already have to deal with the problem of what do you do when these strings are stuck between branches that have to cross. Okay? I will tell you how you deal with that. Very simple. Okay, so let's consider. Now it's a bit simpler to start with the vortex loop side as opposed to the Wilson loop side. It's totally equivalent, but it makes it slightly simpler. Start with a particular vortex loop VMR. So R is the representation of UI minus 1 that's equivalent to the 1D gauge that lives on the defect. And by an integer m, which is the number of D5 branches that are to the right of these strings that realize the vortex loop. Again, the rule is that the real Wilson loop in this case is obtained from S duality and brand rearrangement. But now what happens is that, so here was the original vortex loop, here is what you get after S duality. But in order to read the gauge, you have to move this guy, the D5 brand, through to the right. And it has to cross this fundamental state. So how do you deal with this? Yeah. So the new phenomenon that we have to understand how to deal with is that now we have to learn what happens when D5 brands cross fundamental state. And what happens actually is very tricky, and it has a simple physical picture. Essentially what happens is that this is the local jump, the local move that you have to understand how to deal with. So you have this string that has to be crossed along an S5 brand, but there are fundamental strings in the middle. So the way, in practice, that we deal with this problem is that you have to sum over all possible ways that the fundamental string can split into fundamental strings that end on the D3 branch and fundamental strings that can be attached to the D5 branch. And the reason that this happens is that you should think the D5 branch has an excess of D3 branches on one side. So what physically happens is it develops a throw or a spike, like the bio. So when you move, when it crosses the strings, what happens is the strings can attach to the spike and move off on the D5 branch direction. And this is what's represented by this picture. So when you have fundamental strings stuck between them, what you have to do is sum over all possible ways of splitting the strings between the D5 branches that are being crossed and the D3 branches that you originally were lined. If you translate this into gauge theory language, what this means is the following. First, notice that you have fundamental strings that are ending on D3 branches, which are the support gauge groups, but you also have fundamental strings that end on D5 branches. And this object, what are these objects? So on D5 branches, you support the flavor symmetry. So each D5 branch will do one flavor that the theory has. And therefore, a fundamental string ending on a D5 branch is essentially a background Wilson loop for the flavor symmetry. Okay. So that means that the vortex loop that we started with essentially is a sum over a very specific set of representations that you get by breaking UN minus 1 to U1 times UN, of a sum of flavor Wilson loops that have to do with the strings that end on D5 branches, and Wilson loops that are supported in the UN gauge group. Remember that M was one of the labels that we defined before. So by playing this game, you can find absolutely complete expression of what is the duality This is an example of a more complicated example of a duality map where a vortex loop decomposes into a sum, a product of flavor and gates. And exactly the same logic can be carried out line by line for arbitrarily linear and circular curves, and we did in the paper that this should give you a flavor of how things work. So as you see, once you understand what the rules are, it's extremely simple to derive what the duality map is. Also, once you understand how the representations are encoded into one. So at some point, here we could have stopped and say, okay, this is the duality map. But we wanted to do better, and we wanted to explicitly verify our results by computing expectation value. So I cannot be super brief. Essentially what we did is to compute the exact expectation values of Wilson and vortex operators in this sphere by putting them in this sphere and computing them using supersymmetric localization. So this is a rather technical story that I probably have 2 minutes left to explain, so I will not say very much about it. So what we have to do is to learn how to couple the supersymmetric quantum mechanics that was living localization. And this can be done, and the way this is done is by turning on background fields on the supersymmetric quantum mechanics such that it has the right hooks so that you can couple the quantum mechanics to the 3D theory on the sphere. What is the final answer? Essentially what happens is what you end up having as expectation value the vortex loop. For the Wilson loop, I think you would all know how to write down the answer, at least the formal answer. What you have to do is just do a convolution of the partition function, the 3D theory on the sphere that was computed by Kapustin, Bullet, and Yakov, and convolve it with the partition function of the supersymmetric quantum mechanics that lives on a circle, which it turns out we can identify precisely with the Witten index. So flavor Witten index that you can define as supersymmetric quantum mechanics. That can also be computed by localization in some details that I will not have time to discuss. Essentially, there is a concrete formula for the 3D ST partition function. There is a concrete formula for the 1D partition function in flat space. And when you combine them together and put them in the 3 sphere, they interact with each other in an interesting way. Determined accordingly of how the flavor symmetries of the 1D theory are gauged by the bulk theory. So what we end up having is an integral, essentially a convolution of the 3-dimensional matrix model with the Witten index of the supersymmetric quantum mechanics, with the parameters of the flavor symmetries of the quantum mechanics are tied with either the gauge parameters of the 3D theory or the mass parameters of the 3D theory, depending on how you decouple first. And another example, so this is checking this is a complete nightmare that only Benjamin knows how to do. But you can do it very explicitly. Another example that we've checked, the duality explicit, the very explicit duality map that we found can be checked and it works in all details, and we can precisely see that the picture that we have derived using brains is realized and the expectation values match. So let me just conclude with the last slide. So some of the non-dualities pass the Wilson litmus test that I discussed at the beginning, having to do with the puzzle, how are you even going to match Wilson root when the two theories don't have the same data. In S-duality, the way it works is by realizing that the dual theory has you have the gauge group G, the S-dual theory has the Langlands dual gauge group. So that's how S-duality solves that problem there. In igst2015, the way that the bulk finds the coordinates of the Wilson loops is by having the right difference in the bulk that can sort the Wilson loop representation. And for mirror system, what we find is that it's encoding the way the mirror loops are encoded is in a subtle way of defining a dual operation by coupling a 1D and equals theory to the bulk. And that's how it answers this basic puzzle of where are the mirror loops. So with that, thank you.
Can you comment on whether you can generalize your discussion to 3D equal 2 theories, say mass deformation or things like that? To 3D equal 2 cases by, say, rotating the branes, for example.
Okay, so,
okay.
well, so this is, make some observations. For example, one thing, no, actually, you can apply this in 3D theories. But actually, one of the things that we found in examples is something that is known to be true in pure Chern-Simons theory, which is that if you define the vortex loop by coupling quantum mechanics to the 3D theories, what we can show is that if you integrate the quantum mechanics out, you get a Wilson loop, which is what happens in pure Chern-Simons theory. So pure Chern-Simons theory, if you define a vortex loop by some singular holonomy, it was shown by Cyber and Moore, that this is exactly equivalent to the definition of a Cyber Wilson loop. So what we're finding in some examples is that a vortex loop in a given theory is the same as a Wilson loop in the same theory. But we have, I mean, there are many 3D.
And the last statement works with matters included. I mean, the case with Witten was pure Chern-Simons.
Yes, I'm saying including matter of color.
Other question.
Non-topological theory.
Yeah. So in your map, where you met the vortex loop to the sum of Wilson, when you now take, it doesn't seem to be like totally symmetric. Like usually you map one fundamental option to another one. You now take one of the Wilson loops and apply the Murray symmetry.
You can invert them out.
Okay. Well, okay, so the WN, if you map it back,
Well, it will be a very,
so it's actually not.
well, no one tells you that the map is a map. It's a matter of basis. I mean, we are used to this. So a nice basis to think about physically is this basis. So this basis, we know the BMR, which is a gauge theory coupled with some graphic theory. I know what it means. So if you like this physical basis, you know what you're talking about, then the map is complicated. Oh no, can't be complicated. The example in the map is still a Wilson loop map, a Wilson parallel loop, and etc. I just wrote this example because this is the generic complicated case where the map gets slightly different. But very complicated.
Any other questions?
Maybe I can. Yeah, so is there an AGT dual for this 3-dimensional plus 1-dimensional piece? It's in the 4 plus 2 plus. So in the case of 4 plus 2, there is a dual.
So there is something called the 3D duality. I think there one should be able to say something in terms of data, but it's not AGT. So this is a statement that but the problem with that is that I think the 3D duality only engineers using 3D hyperbolic geometry. So very specific 3D gauge theories. None of this type. So none as rich as this type. But I think for those you could also think of enriching the hyperbolic geometry with, well, maybe you don't know. I mean, you can add some line defects and so on that would, under change of triangulations, give you the mirror.
Yeah. So in fact, we are writing a paper about
okay, good.
the defects about 3D.
With the non-linear theory.
Yeah, with both are doing a non-linear. So TSC and TSC. It's a pretty straightforward.
Okay. So I think we meet again at 20 past, and it's
then we can use the fact that these three branes can actually end vector. So we may consider a setup where there are n, say n minus k branes equal to and then there are KD branes, the three branes, n on phi. So on the right we have gauge symmetry SUN, and on the left it's broken down to SU and minus k. Alright, so what is the field theory description of the setup? Well, should be some sort of fixed mechanism, but we also want to preserve conformal invariance of the theory. So the Higgs expectation value that breaks the symmetry should be taken to be. So we're sitting at energies that are much lower than the scale set by the expectation value. So here, expectation value of y, well, there are lots of scalar fields that can break symmetry and plus 4. So on the left they are right. And on the right they should relax according to the equation solution. So we consider a field configuration that is defined on the positive semi-axis. So here it's infinite, and then it relaxes to 0 on the other side of the domain. And so this phi classical should solve the equations of motion for the Lagrangian. So let me write down these equations. So I'll review a long story. It's probably first who started working with this was the School in the 90s. And so since this theory is supersymmetric, it's possible actually to solve first order differential equations instead of second order ones. We can, instead of this second order equation, solve the first order one. And this equation is actually has a name to it. It's called NUM equation. And it describes monopole solutions in two polypole monopoles in a situation where there's a potential. This is well, it's consistent with the fact that if you view these three branes as solitons on the road going to be fine, then they behave as monopoles. And so in the dual picture, what we consider dynamics, the road going of the three brane, they are described by the construction. Anyway, so this will not be really important for me. What will be important is just the classical solutions that one gets. And this is so it's easy to check that well, the z dependence So our goal was to somehow relate this story to integrability. And to connect integrability, we need to consider non-protected operators. And then, well, the structure becomes more complicated, but also more interesting. And so far, we were able only to consider the simplest case where k is equal to 2. So I will concentrate on this simplest setup, where even then one finds quite a lot of structure. When we consider unprotected operators, I'm talking about single trace operators at RGM, so they can be mapped to spin chains. And so the question is, what is this one-point function in the spin chain diction? So if you take an operator that, well, is described by some wave function for the spin chain, multiplying the fluid monomials, and so this is the wave function for the spin chain. So first, to consider conformal operators, this has to be beta wave function. To compute then the correlation function in the presence of the defect, we simply replace this twice by their classical values. And you see that the one-point function then has the correct dependence, which is not surprising. And for the coefficient C, we get, so if we recover the correct normalization, so this will be, let me see, consider two fields Z and W, which are identified with spin up and spin down. And so let's take the let's consider the situation where Z is phi 1 plus phi 4, and W is phi 2 plus phi 5. And then we consider the case where phi 1, 2, and 3 have expectation values, which are equal to t1, 2, 3 divided by z, and then phi 5, 4, and 6 are equal to 0. And also we consider the case of k equals 2. Then, well, Ti can be simply taken to be half-Darwin matrices. And so the MPS state then, well, at first it looks pretty simple. So we should take a product over all stacks. So we associate spin up with the matrix T1 and spin down with the matrix T2. So then we take the product of all sides, and then we take the trace index of the space. So it's usually done in the algebraic methods. The construction is very simple. But notice that here the auxiliary space with a physical meaning originates from the color space of the original quantum field theory. And so, well, what do we get at the end? First, it seems that the answer is almost trivial. Because, well, so first of all, if you take a product of an odd number of power matrices, of course, the answer will be 0. So,
That's a bit complicated before you state it was like an unknown.
yes, so we take product of t's. So T1 is now
The state is well.
well, look. So in this setup, once we see phi 1, we should insert z for 1. For the t, if we see phi 2, which is spin down, insert z. Then we take a product and a trace. So that's what's written here. Right? So here's the spin up at side L. We insert T1. Otherwise, we insert T2 and take product and the trace.
So in simple language, as a spin chain, is this three-rounded condition?
Cyclic is, well, it's periodic.
It's copy spin chain, you have a boundary.
No, the spin chain is periodic spin chain without size. So this looks as a very simple state. So first of all, yes, it vanishes if L is odd, so L has to be given. Now,
Sorry, Kostya, what happened to T3, for example? Why is there no
T3, well, here doesn't appear because we chose such and such operators. So we chose operators that only contain phi 1, phi 2, and no phi 3. so it's also possible to say that M should be even, so the number of down splits. Well, why is that? It's again for the same reason. So the strategy to compute these traits, sigma 1 and sigma 2s, then you regroup them using anti-commutation relations, and so the power, the odd power of sigma 1 is sigma 1, the even power is 1, same for sigma 2. So you're left with sigma 1 and sigma 2, the product is sigma 3, trace is 0. Okay? So M should be also even. Then the state should be cyclically symmetric. So total momentum is 0. And also, so if all these conditions are satisfied, so again, after this regrouping of sigma 1s and sigma 2s, what we get is that the wave function is equal to either 1 or minus 1. And of course, there are also all states here. So it's a linear combination of all possible states with arbitrary even number of up and down spins with the coefficients which are just 1s or minus 1s. But now how to choose 1 and minus 1 depends on how you anti-commute the G1 and G2 matrices. So it's actually not very easy to see the pattern there. So the wave function is, well, you cannot write it as simpler than well, actually, it's possible to understand the structure behind it, but not in so simple ways. All right, so this is the state that characterizes the defect, and I guess an interpretation of the state is that it is a boundary state associated with the defect rate. So if we consider this state at any coupling, stroke coupling, this should flow to the boundary close to its state, and well, psi then corresponds to the state of the fundamental closed string. So they are completely just an overlap of the string state with the boundary state. So, so the psi should be some beta state. There is, so to have a non-zero overlap, it should also have even number of excitations and total zero total momentum. However, these are not the only constraints that one has to impose. There is a less obvious constraint that the state should be what's called so all the rapidities in this state should be should actually be paired. So they should adhere in mirror symmetric pairs. So why is that? So this, of course, will automatically satisfy the total momentum constraint, but this is not the only way. So there are two types of physical states, physical from the point of view. N+4 in the Heisenberg spin chain, these are states which well, satisfy this momentum constraint trivially, and then one can also balance the zero momentum constraint such that well, the states are not paired, and so by symmetry, then the state that but the claim is that those states have trivial overlap with APS, and to see this, one has to one can prove that the matrix product state is annihilated by the third charge in the interval hierarchy. So this is a bit of a calculation, but it can be done pretty explicitly. Of course, this is not an Hamiltonian, but the third charge acts trivially, so there is a selection, there is a rule for the and so this states which have non-zero overlap should have zero, and these are precisely unclaimed states of this form. So now, what we need to do is we need to compute the overlap of this beta state with the state of this form. So again, this is one can do it in mathematical for, I don't know, length 8 or excitations easily. With some trickery you can use for any length, I don't know, up to 10 excitations. But of course it becomes more and more complicated. But as in this story with the frequent functions, there is an internal representation of frequent functions was first shown by Koda. And here, there is, so we were unable to find so how should I say, we couldn't find a formula for the overlap of MPS with beta states. But the formula that works, was known. So there is a formula that was known before, but it was just not known that it has much wider range of applications. So let me this the equation. So the claim is that the structure constant, and it depends on their affinities. And now I assume that all affinities are pairs. So and any pair once. So for instance, one can assume that all affinities are positive pair bar. So this is equal to 2. It comes from the phrase. M2 over M2 matrices. And you see on this introduced two types. One of them is like the non-matrix with a plus and with the minus and something like that. So anyway, so this formula is strictly speaking, this is a conjecture. We can only prove it in the case where the number for the half-field state. So when the number of up and down spins is equal,
boundary will be like a boundary string from the definer. It is floating emission by the definer with the boundary string.
Presumably. I mean, so far I'm not able to check this because to do the classical computation on the string theory side, we need large K. So the formulas that are on the blackboard are for K equals 2. So the first one has to generalize to large K, and then probably want to do something similar to for the Riemann thing.
Sort of continuity question we could discuss. So if I just wanted to do the calculation, as you say, you can do the calculation.
Can you speak on the microphone?
Oh, sorry. Can you hear me now? If I wanted to do the calculation in string theory, which I guess is what I'm doing, what would be the topology of would it be a sampler or a disk?
So there's a in alias you consider a deep array.
No, just in flat space. If I really wanted to do the same calculation as you do in the gauge theory, but do it in the flat space string theory.
This can be on the definer.
Well, anyway, so there's a deep array.
This on the definer with an insert.
Insert an operator that emits the string, and the string ends on the break. Right? So we need to compute this step of that. So this is all this, and this is the defined
The operator OX is from an open string and in flat space. I don't know the AES description.
Well, it's a closed string. It's spin chain operator.
No, before you do any holography, right, you just have a D3 brain.
Yes.
There, the operator is an open string operator. Some operator, some open string that is a D3 brain.
I'm not quite sure I understand the question, but single trace operators larger than do closed strings propagated in the space.
Yeah, I think you're
I'm just asking flat space in the diagram that before you do any holography,
just in the
Yes.
section.
just in the brain intersection.
Well, this is useful as a picture. I'm not sure it's useful.
No, I mean, the low energy theory there is the gauge theory, right? So I just wondered if I wanted to do a calculation in the string theory rather than the gauge theory. In this.
But how would you do the two-point function in the problem?
That's what I'm asking. What is the corresponding?
If you don't have a defined array, what would be the
Well, it's just a two-point function. Same as in the gauge theory, except it's in the string theory. So it's a two-point function on a disk with two open strings inside. Two open string operators inside. So I just want to know what's the.
I think it should be the same, but with holes ending on the D3.
With a hole. So a topology. So you have a topology of a cylinder.
That's one those from.
That was.
Okay, one more question here.
So what's the formula for K plus minus? I think is it correct that for some regular operators you will get an old propagator like UI minus J minus K plus 1?
integrability will be an important ingredient, and all of you are welcome to participate in this program. So please apply, and I hope to see many of you in Stockholm. Thank you.
Okay. So final talk for the morning session is Simone Tombi about generalized X theorem and the epsilon expansion.
Okay, thank you very much for the introduction, for the invitation to speak. It's a very nice meeting. So as you can guess from the title, I'm not going to talk about integrability, but I hope it's okay to take a short break and discuss something slightly different. So the topic will be about C theorems in general dimensions and sphere-free energies in general dimensions. And this will be based mainly on these two papers. One paper I wrote last September with Igor Levanov, and another paper which appeared very recently also with Igor and two students. Does it work?
Yeah.
Yes? Do you hear me? Okay. Okay. Good. So let me start with some review of very well-known facts about appearance in various dimensions. It is still not working. So it is an interesting and deep problem, but we're here to define some measure of degrees of freedom, some quantity which decreases under normalization group flows. So it decreases as you flow from UV fixed point to some IR fixed point. And in two dimensions, this problem of finding such a quantity was, as very well known, was solved by Zamolodchikov, who constructed explicitly a C function which decreases under the RG flow and is stationary at fixed points. And at the fixed points, this quantity just coincides with the central charge of the CFT. And the central charge is also related, of course, to the trace anomaly of the CFT. If you put the CFT on a curved background, then the trace of the stress tensor is non-zero. It's proportional to the Ricci scalar of the manifold. And the constant of proportionality is the central charge where there's this factor in some conventions. Another way to extract this central charge, which is equivalent to this, and which would be the one which more relevant for the rest of the talk, is to use the sphere partition function to be on the Euclidean round 2 sphere and compute the path integral. So compute the free energy minus the log of the partition function of the sphere, and in two dimensions this quantity will have a term which depends on the logarithm of the radius of the sphere. So R is the radius of the sphere, we use some UV normalization scale. And the constant of proportionality is related to the central charge. Okay? So if we look higher dimensions and look at trace anomalies, for example, in 4 dimension, and there it's well known that the trace anomaly has two terms. One term is proportional to the Euler density, and the constant of proportionality is denoted by A. And another term is proportional to the square of the Wald tensor, and we mentioned is this A. And in particular, it's this A that can be extracted from the Euclidean partition function on a force field. So one explicit way to extract this A, in the same way as we did here for C in 2 dimension, by Cassini and Puerta to actually prove this inequality for our three-dimensional CFTs. Okay, so in the Cleveland proof and stuff, we also suggested a natural generalization, this to higher odd dimensions, and so this is much more speculative. There is no. What they observe is that if you just take the same quantity but with some kind of alternating signs, then that quantity is conjectured to decrease under Argand flows. So it is f in 3 dimensions, it's minus f in 5 dimensions, and so on. And later in the talk I will give some explicit test of this in 5 dimensions. Okay. Any questions so far? Okay. So as a comment, notice that there are also other natural quantities that we could think would be measure of degrees of freedom, like for example CT, the normalization function of stress tensor, or C thermal, the coefficient of the thermal free energy on the plane. Those are very natural objects, at least naively much more natural than F. But there are counterexamples that basically show that these two quantities do not always decrease under Argand flow, so they are not good PC functions. In 2 dimensions, F, C, CT, and C thermal are all related, but in 3 dimensions they are not. And what is really more similar to a central charge in 3 dimensions is F. So it's clearly then an important problem to determine what F is in some CFTs. So it's a number that we can assign to any CFT, and it's important to know what this number is. If we want, for example, put constraint about which CFT can flow to what. So is F actually computable in practice in explicit examples? Well, it's definitely relatively easy to compute for free fields. So if you take a free master scalar or free fermion, then you can compute it explicitly, just on a loop terminal on the sphere. You get these funny looking numbers, combinations of log 2 and 3. So this is for a scalar, this is for a fermion. But in general, for interacting CFTs in 3 dimensions, it's very hard to compute this F. So as it was discussed in the talks already, by using localization, you can compute it in some supersymmetric cases. But there are many non-supersymmetric cases for which a direct calculation is just out of reach because they are strongly coupled instruments. So one goal of the talk will be to try to find some method to actually compute this F in some interesting 3-dimensional CFTs. Okay, so one example of a simple but yet complicated CFTs is the interacting ON model. So this is a textbook example of an interesting CFT in 3 dimensions. If you take n scalars and you add a quartet interaction, in 3 dimensions this is a relevant interaction, and there is an RG flow from a free theory of n scalars to an interacting IR fixed point, which I will call the critical ON model. In the case n equal 1, the model is just the 3-dimensional Ising model, which was in the news quite a bit recently because of some progress in solving it by using the conformal bootstrap techniques. Unfortunately, conformal bootstrap techniques, at least as far as we understand so far, they're not able to tell you anything about what F is, because F is not something that is accessible from conformal bootstrap. So what we want to do is try to find some other way to compute F for this kind of models. These models also play a role in the ADS-CFT context because they are dual to the Facilier higher spin gravity in ADS4, and the 2 fixed points of this model, the free UV fixed point or the critical ON model in the IR, are dual to the same higher spin theories, and the difference amounts to changing boundary conditions on one box in the field. I'm not going to talk about this. Just wanted to mention it, but it would take a whole different talk to extend on this. So let's move on with scale free energies. So for this model, as I said, there are no explicit results for finite n. All that is known is about Largenius functions and only to leading order, to order n to the 0. So for this fixed point, you can compute f in a Largenian expansion, and the result don't have a proof, but all the examples that we have obey this fact. And what's important to stress that I'm talking about unitary safety. So this is true in all unitary flows. If there are some unitary fixed points, then this does not have to hold. And it doesn't hold if these are not unitary. And also another comment, this is just a statement about the value of this quantity at the fixed point. We're not constructing, as the homological did, some function which interpolates along the RG2 as a function of scale. Just telling how to compute the number at a fixed point and compare to fixed points. So the problem of constructing some interpolation function is more complicated. And it's not something I'm going to discuss. Any questions so far?
Is there a meaning for them when you go into a different dimension, in theory that somehow will change dimension?
Not as far as I know. Yeah, we're considering flows in some given dimension in CFDs that live in that dimension. And we're not considering flows that brings you from one dimension to another.
But if you have a function that is defined for all of them,
Yeah. Maybe you could. We should actually reduce dimensions. Yes, we didn't think about that. Okay, so yes.
The derivatives of f theta with respect to d at the integer d have a physical meaning?
Not as far as I didn't try to compute the derivative with respect to d. Not sure. What's the idea about the derivative with respect to
I guess you could find a different interpolating function that is
Oh, okay. So one thing that I should say, this interpolating function, I mean, this choice of sign is for convenience. I mean, I could further multiply this by a function of dimension, and I wouldn't change this statement. It's important that there's this oscillating structure, and also the definition is such that I just get f in 3 dimensions. That's all there is. Even there, you could say that it's 5f decreases in nonsense, right? You could further multiply by anything. It's a convenience. All right. So to see more explicitly what is a tilde does, we can start from free fields. So, for example, consider a free scalar on SD, and you can compute this at f in any dimensions. To stagger the details, but so it's just a determinant operator. This comes from conformal coupling to the curvature, and this determinant is explicitly in terms of, well, can be written as some integer, just as some integer representation. And one can see this factor of sign popping up here, which is essentially responsible for these poles that you have in given dimensions, and for the alternating sign structure, because you have 1 over epsilon minus 1 over epsilon, depending whether you are forced. So for example, in 4 minus epsilon, this gives 1 over 90 epsilon, and 1 over 90 is the A anomaly coefficient of a scalar in 4 dimension. And if you set d equal 3, you get instead the numbers that I wrote before. So this appearance of sign was one of the first hints that we should, maybe it's a good idea to multiply that, I guess, factor and get rid of this. exponential. You determine that by extremizing this quantity with respect to delta. Okay? So this is some version of F maximization, which interpolates between 2 and 4. And you can show that this quantity here is relatively clever in the sense that it interpolates smoothly between known objects in 4D, 3D, and 2D. So in 4D, for example, this quantity is just a well-known cubic polynomial which gives you the polynomial in terms of the R charge, it just comes out from this. In 3D, it's just this function curly L that is defined in this localization.
the theories in fractional dimensions are in general non-uniform.
Well, there's some form of subtle unitarity, yes. I think maybe the safe statement is that if a theory is the dimensional continuation of a unitary theory in integer dimensions, then this should hold. But yeah, that should be clarified. It's not clear what that. So I think you're thinking about this fact that you can show that there are some very relative high dimensional operators which have negative two-point functions, for example. It's not clear how that affects this. So far, we've never seen a violation of this, even in fractional dimension.
So normally the bootstrap people put error bars on their results. Do you know what they are? Do you have some estimate?
We can estimate the error bars by doing this summation in different ways, by using different arrays, slightly different things, and we can kind of estimate the spread. And I think it's, if I would want to give you a number, it would be about 0.01. 0.01.
What were theirs?
So something like between.
What were the?
Thanks. Well, I think they're much lower because they do all these digits, but I don't remember what they actually call. This is just meant as a qualitative comparison. They're not supposed to be the same.
Alright, so let's thank all the speakers in the morning.
Hi, two announcements. First about the dinner tonight. Remember, if you bring a guest